Hi, my name is Percy. I hope you guys are having fun developing your own robot following our last video. Today we're going to dive deep into the training code. I'm going to show you guys how we implement the IL policy and why we do that. Now we can go into the IL policy part. These are the contents we're going to cover today. Repo structure, I'm going to introduce the folder structure of our code, robot model, including the UIDF model and other simulation parameters. The PPO algorithm is the main IO algorithm. I'm going to tell you guys what parameters we set it. We set in the algorithm. Events is some randomization, startup, reset stuff. Observations is what the neural networks has in the observation. Rewards is how we define the motion we expect, we want. And actions is what the output of the neural networks. Now let's go into the folder structure. So I'm going to introduce the main files in the folder. So the first tools we need to check is the play py and train py, which we use to train and play the IO policy. Check robot, you can visualize the robot. Convert MJCF and convert UIDF. You can use these two files, convert MJCF file and UIDF file into the USD file, where USD file is the main file format used in Isaac Lab. List environments. You can list all the possible environments implemented in this folder using this file. And now let's go to the UIDF part. So this is what a standard UIDF file format looks like. We have a UIDF file to connect. In this UIDF file, we have the geometric information and we have the physical information like mass, inertia, this kind of stuff. And these STL files are the meshes for visualization. And now we are in the IR training part. So the first thing we can see here is the deep robotics PY. So in the UIDF file, we define the physical and geometric information, but there are other things we need to change in the simulation. So like how we model the motor, like what are the PD gains, what are the lag of the motors, this will be defined in this file. And now we can go to the main IO policy file. So our IO policy includes an environment for the robot to interact with and the IO algorithm to dig information out of the data it collected when interacting with the environment. So this rough environment config and flat environment config defines our environment, and this RSL IO PPO config, this one defines the IO policy parameters, how we're going to dig the information from the data. And these MDP folder, MDP is short for Markov Decision Process. It contains what needs to be defined in a Markov decision process. Like the commands is the track, the linear and angular velocity we need the robot to track. The curriculum is how the training is going to evolve through different time. Events is like randomization, reset. Observation is what we put inside the neural network, and rewards is how we define the expected motion. So this is the main structure of the folder. Now let's introduce the deep robotics PY file. In here we define our robot. So I'm going to introduce the important parameters here. So let's go from the start. This fixed base is where we define whether the base will be fixed or not. If it is true, the base will be fixed in the air all the time. You cannot move it. And it will be just leg swinging in the air. Merge fixed joints is that when defining in the UIDF file, there are some fixed joints. If you set this to be true, the fixed joints, one fixed joint connects two rigid bodies, right? If you set this to be true, they will be merged into one big rigid body. Sometimes this can make the simulation faster. Replace cylinder with capsules is that, so in a cylinder it's like this one, but it doesn't have anything on the sides. If you replace it with capsules, it's going to have a little two bolts on the sides of the cylinder, and this can also speed up the simulation. It's a kind of optimization in Isaac Lab. Asset path is where we put our UIDF file. And let me see. Disable gravity, you can know from the name that if you set it to be true, no gravity is going to be applied to this rigid body, to this robot. And let me see. Okay, these are not very important. Okay, for this solver, position iteration count and velocity iteration count, we usually set this one to be 1 and this one to be 4. If you want your simulation to be more precise, you can increase this number, position iteration, like how many iterations you have when you're solving a partial derivative equation, or so when you just iterate through the equations. But if you increase it to be very large, it's going to slow down the simulation. It's more like a trade-off, like how much you want for the precision or how much you want for the efficiency. And for the joint drives, usually we set the stiffness and damping to be 0, because there are usually some compensation in the joints. And when it moves in the reality, the stiffness and damping is pretty close to 0. Okay, now let's go to the initial state. Initial state is where the robot is going to start from in the simulation, like one robot goes into the environment where it's going to be. So the pose, the x, y, 0 is okay, z is 0.35, because that's the usual height of the Light 3 robot when it stands on its feet. And the default joint pose is, so the 4 legs are symmetric to each other. The values for the joints are the same. We only need to define 3 of them. So 1, 2, 3, right? It's 0, 0, and negative 0.8 and 1.6. And the joint velocity, the initial joint velocity, just set it to be 0. Just you don't have to make it move at the start. Soft joint pose limit. This one is so it has joint pose limit, right? You can define it like at what point it reaches the limit, and you're going to give it some penalty. So we set it to be the 0.99 of the limit. And here are some very important parts, the actuators. This part you need to define it very carefully, so because this part can introduce a lot of center gap. So in here, for our hip X and hip Y, which are the 2 joints here, the effort limit is this one and velocity limit is this one. And these are the design limit of the hardware. If you want to implement our algorithm on a different robot, you need to check their limits. You don't want to move past this limit, because it's going to burn the motors and the robot is going to be broken down. And also in here, the stiffness damping, it doesn't mean the actual stiffness damping. Instead, it means the PD gains. Stiffness is the P and damping is the D. And also the friction, we just set it to be 0, because for our robot, friction is not that large. And amateur is the value you added to the diagonal part of the inertial matrix. Our motor is very small, you don't need to do that. But if you have like a bigger motor, like our other products like X30, M20, you may need to add a little bit, because if you set it to be 0, the symmetry gap is going to be pretty large. And the important thing here is that this max delay is 5. What does this mean? So in simulation, there's no lag, but in reality, there are a lot of lags. And for our robot, the lag is usually between 0 to 25 milliseconds. So in our simulation, the simulation physics steps is 5 milliseconds. And this max delay defines that how many physics steps is going to be delayed. So we set it to be 5 here, the max delay. The mean delay is 0. So the lag is going to be randomized between 0 and 5. Like how many physics steps is going to be. And our knee joints are defined a little bit different. So, but the main parameters are the same. Okay, so this is how we define our robot model in the simulation. Now we can go into the IO policy part. So we are using the very classic PPO IO algorithm here. The PPO algorithm is very powerful. We don't really need to change much. So I'm not just going to introduce the part of the algorithm, the part that we need to change here. So these parameters, like max iterations, is how many epochs we're going to let it train. We set it to be 20,000. Usually like 10,000 is enough for a quadruped locomotion test to converge. 10,000. All right, remember that number. If it passed that, either you have a very complicated task or something's wrong. The safe interval is we set it 100 here, like for every 100 epochs of training, we're going to save the checkpoint, just in case you want to check how the performance will be during the training. And the experiment name is just what we name the experiment, what we name the training. And the policy, the neural network is defined here. The people algorithm use an actor-critic kind of shape of the neural networks and design. And the dimensions are written here. It's pretty standard, usually for a locomotion task, either for quadruped, wheeled quadruped, humanoid sometimes. Humanoid, you can just increase it a little bit, but it's just increase all the numbers here by 2. It should be enough for locomotion without vision task. The activation function is we use ALU here. There are other functions, activation functions you can test with, but they don't make much difference according to my experience. And for the PPO algorithm part, this part is usually pretty standard in a locomotion task. We don't touch it very much. If you guys want to see it, you can read the PPO algorithm paper or find other videos introducing the PPO algorithm. We're not going to elaborate on this part too much in this video. Anyway, PPO algorithm is a very powerful one. It's much more than enough for a simple task like a quadruped locomotion. Alright, and this part of the config, you can modify a little bit if you want. Like this is the flat config, and the rough config is the one we just defined here. So in the flat, you can just probably reduce it. Somehow I increase it here, and just going to change a little bit. And you can also change the name, just inherit from this class, and then now you got like 2 environments here. Now we're going to go into the environment definition part for our IR policy. This part we're going to cover events, observations, rewards, and actions. So let's go first to the events. What is events? Events is what's going to happen during the IR training process. And let's go through it, and you guys will see what it means. So the first event we define here is randomize reset base. So from the name, you know we're going to randomize the base when it is reset. So sometimes at the very start of the training, the robot is going to fail very easily. You just kind of randomly test it, randomly interact with the environment. When reset the base, when we reset the environment, the robot, we're going to change the position, rotation, velocity of the base. And this is where we define it. The position range, like X, Y, is just horizontal. The Z, we set it to be the same, because this is a very simple task. We don't need to give a lot of randomization. We just needed to walk around on even terrains. So we just set it to be 0. And this 0 is sufficient for this task. And for the roll pitch yaw, it's going to, so roll pitch is also X, Y. It's going to tilt it like this. This, we don't set it to be very large, because as I just said, it's a very simple task. It doesn't need that much of randomization. Fewer randomization can lead to faster convergence. So as for simple tasks, this is okay. For complicated tasks, you usually need to have a curriculum. And the curriculum, you also need to randomize from small ranges to large ranges. That we'll cover later. But for the yaw, we can increase it a bit more because this is around the Z-axis, so you can just move like this. This is okay. It doesn't, like wherever the head points to, it's totally fine. It doesn't include any difficulty to the training. And the second environment. The second event we define here is the randomized rigid body mass. As from the name, you guys can know that we're going to randomize the mass of the rigid bodies, the links, right? So when using this one, we're going to define the name of the links. So in here, I'm using all the links we have, just give it a little bit of randomization. And if you click inside here, you can see where is exactly the values of the definition. So we define the mass randomization to, like this is scale, right? To be the 0.7 and 1.3 scale of the original mass defined in the UIDF. This is actually a pretty large range, just in case that the actual mass is smaller, lighter, or heavier than the values defined in your UIDF file. And recomputing inertia is to increase the mass, the inertia is going to be different, it's going to recompute the inertia for you when you define it. Okay, so this is this event. And the third event you're going to see here is randomized center of mass position. As you guys can know from the name too, we're going to randomize the center of mass. So the range here is 0.3, xy, and 0.02 for z. And we are only going to randomize center of mass for the base link, because base link is the biggest one. Usually this one has difference. Other links are very small, it's okay. It's not that important. All right. And in here we are not randomizing applied external force and torque, and we're not pushing the robot too. Like I said, this is a very simple task. We don't need that much of trick to make it more robust. But if you guys are going to use a more complicated task, like you're going to do like a backflip or other stuff, you can add these events into it. And the third thing we're going to do here is to randomize the actuator gains. So the actuator gains are the PD gains here. And we're also using all the joints. We're going to randomize all the joints PD gains. Let's click in here. So the range is also 0.7 to 1.3. It is also very large because the PD gains can be different. Like the motors, in simulation the motors are very ideal, but in the reality it's going to be affected by the current, by the voltage, by the temperature, a lot of things, and it's going to change. Maybe this second is the same, next second is going to be larger, the next second is going to be smaller. So we're going to randomize it a little bit so the neural network we trained can be robust against these kind of changes when deployed into the real robot. Okay, so this part is for the events part. Now let's go into the observation part. So our observation for the neural network is 45 dimension, and the output action is 12 dimension. The output action is the desired joint pose of the robot, and let's go into the observation of the neural network. So if you click here, you can see where our observation is defined. So in here we have the base linear velocity of the base, angular velocity of the base, projected gravity, which is the gravity in the robot's frame. You can see whether you can tell from the projected gravity whether the robot is standing upright or not. And the velocity command, we have three components here: the x and y linear velocity, the angular velocity, and these three are the commands the robot is going to follow. It's going to track these commands. The joint pose, we have 12 joints. It's 12 dimension. Joint velocity, also 12 dimension. Actions, which is the output desired joint pose of the robot, also 12 dimensions. And high scan, we're not using high scan here, but you can define it. So there we have 3 for base angular velocity, 3 for projected gravity, 3 for commands, 12 for joint pose, 12 for joint velocity, 12 for actions, which is 45 dimension in total. And this is our observation and our actions. We also have the scale for it. So why do we need to have the scale here? Because the magnitude of the observations and actions are different. We want it to be around the same magnitude. This can make the training process go smoother. The neural networks are good at predicting values that are the same magnitude. If you have like a 1 and a 10,000, one of them is going to be very hard to predict. So in here, we set our base angular velocity to be 0.25 and our joint velocity to be 0.05. Usually velocities are pretty large in magnitude, so this is why we're going to reduce the scale to make it look the same with other values. And also the joint pose, joint velocity, we need to specify which joints we are using. So in here we are using all the 12 joints. And for the actions, it's also the same. Some of the actions have smaller outputs, some of the actions have bigger outputs. We're also going to specify to change the scale of it. In here we set 0.125 of the hip X joint and 0.25 of the hip other joints other than the joints other than the hip X. So the output of the neural network is going to multiply by this scale, and after multiplying is going to be the actual joint pose, right? Also the same for the observation. The raw observation is going to multiply by the scale and then feed into the neural network. And also the actions, we also need to specify the joints, and the joints here is still going to be all the joints we have. Alright, so this part is for the observation and actions. Now we are going to the reward part. For you guys who have been doing some research in quadruped locomotion control, you know that reward shaping is very troublesome and very engineering heavy. So in here, we're going to provide a set of parameters, a set of reward parameters that's going to produce a pretty good motion. And I'm going to explain what's going to happen if you change this value too large, too small, and how they're going to couple to each other and how they're going to affect each other. Okay, so the first one is this action rate. Action rate is the difference between this action and the next action. So we don't want the action to change too fast, otherwise the robot is going to be very shaky, and we're going to penalize this kind of action. And additional information is that each reward function has a function, like a constant and a weight. If the weight is higher, it means this one is more important. And the actual reward is the weight multiplied by the previous reward calculated from the reward function. Okay, so the next one is the base height. The base height is the desired base height of the base, desired height of the base. So this one is usually pretty important, so we set it to be 10. And another thing is that if the weight is negative, it means it's a penalty term. We set it to be negative, and the PPO algorithm is going to try to minimize it. If it's positive, the algorithm is going to try to maximize it, right? So the base height, we want it to be 0.35. If it deviates it, we're going to give a penalty. One case can happen here is that maybe you tune the parameters a little bit and the robot can only traverse at a very low posture. And even though you increase the weight a lot, it still cannot get up. One trick here is that you can change the desired height to be higher than the actual height, like 0.45 here. Then the robot can, it still have a distance, maybe 0.1 meter distance to the 0.45, but it's traveling at a 0.35 height, and this is going to be what we want, right? Sometimes this can help for like a corrupted set of reward parameters, okay? So the next one is the fit air time. So we want to increase the long steps. We don't want it to this is something we don't want. So we set it to be 0.5 seconds here. This means that the steps are going to happen like every 0.5 seconds. This is like okay frequency for steps. And we're also going to penalize the feed air time variance, which means that, okay, maybe one leg steps at 0.7 seconds and the other one steps for 0.3 seconds. Okay, they said we're all pretty close to the 0.5, and that's okay, I'm not going to change anything. But we don't want that. We don't want like da-da. We want it to be da-da. So we're going to penalize the variance between the feed air time. We want it to be the same, we want it to step like equally to each other. So this is what the feed air time variance means. And the feed slide is that when it steps on the ground, it kind of just slides, right? So we're going to penalize that using the feed slide. And the standstill is that when it doesn't have any command, we hope that the robot can just stand there exactly, no moving at all. So in here, we implement this standstill reward function as the joint deviation to be the default joint pose. If it deviates, it's going to be penalized. And this can make sure that when no commands happen, actually we set the command threshold here to be 0.1, which means the L2 norm of the commands, like 3 commands, is less than 0.1. It's going to just stand there. The next thing is the feet height body. So the feet height body is the height difference between the feet and the base. So you guys may be wondering that why we set 0.35 here, which means that, okay, the base height, desired base height is 0.35, minus 0.35 is going to be on the ground. So this is why I just mentioned that sometimes it cannot give like what you want just by specifying the desired height like 0.25, right? We want the feet to be 10 centimeters above the ground when stepping. So in this case, we need to push a little bit harder than where it should be, and it can give like a okay result. And also, this one is not enough. We have another for feet height. Like this is the actual feet height we want when stepping is like 5 centimeters. It is still too low for the actual case. We want like 10 centimeters. With, like I said, need to push it harder for it to give us the okay results. And the next one is the contact forces. So we hope the robot can step on the ground gently with a light touch. So we're going to penalize the contact forces. The smaller, the better. Okay, there's another term I want to introduce here, is that the linear z velocity, right? So z is this linear velocity. We don't want it to move like up and down. We want it to travel smoothly. So we're going to penalize the velocity in this axis. And the angular velocity for x, y, right? So x, y is this one, y is this one, x is this. So we also don't want that. We only want it to like this z angular velocity. So we're going to penalize the other 2 axes. We just want it to move, when it rotates, just only the z moves, and that's enough. And these 2 terms are the track linear velocity. These 2 are the most important one. When giving the commands, we're going to need it to track the commands, right? 2 linear velocities and 1 angular velocities. And the undesired contacts here, so we have the undesired contact. We don't want it to just roll on the ground. Well, actually it can, but for the simple case like this, we don't need that. So we just want it to move around, and that's okay. And these joint torques is we want to penalize the torque of the joints. We don't want it to exceed the torque limit. If it exceeds, it's going to burn the motor. The joint acceleration is the acceleration of the joints. We also don't want it to be too big because it's going to increase the temperature of the motor, which can also result in burning the motors. Joint deviation for the hip X is that we want us to step vertically, touch the ground. We don't want it to like this or like this, right? We just want it to vertically step on the ground. And this means that this hip X motor, we hope it to be close to 0. So this is why we said, okay, if you deviate from 0, you're going to be given a penalty. And joint power, also the power of the joints, we want you to have a better duration. So we're going to penalize it. Oh, you're spending too much power, you're going to be penalized. And you can learn how to like save the batteries. And this flat orientation is for the orientation of the base. We hope that it can. So we're going to penalize any orientation on the x and y axis. Only it moves z, right? So if you tilt it like this, it's going to be penalized. Okay, and this is all for the reward function part. Okay, so this is all the content of this video. I hope you guys have any fun. I know it's absolutely not enough about what we can cover in the video. If you guys have any questions, just join our Discord server or ask it on the GitHub. We are very happy to answer them. Thank you.